So we are finally getting to the point where we are moving on from derivatives and we are starting the next thing, which is integration. And before we really get into integration, we just have to start looking at curves and the area underneath them and the different ways that we can calculate things. So the title of these notes is going to be Area Under the Curve. And in parentheses, you can write Riemann Sums. That's what they're called. All right, so we're going to start off looking at a situation with just a typical parabola, and we're going to explore it a little bit, and then that idea is what we're going to work with more tomorrow in class. So we're going to say, given that y equals x squared, estimate the area under the curve on the interval, the closed interval from 0 to 1. So when we talk about the area under the curve, what we actually mean is the area between the curve and the x-axis. So if I was to graph this, we'll say this is 1. And if we were thinking about a parabola, if I plug in the point 0, I get 0 squared, which is 0. If I plug in the point 1, I get 1 squared, which is 1. And then we know a parabola look, oh, it's not very curved, looks something like that, right? So the area underneath that curve would be this part right in here, right there. Okay, so over here, and eventually when I say the area under the curve, it will definitely be in your brain that it's between the curve and the x-axis. But for right now, it might be good to add to your notes since we are new to this. So between the curve and the x-axis. All right, so go ahead and write down a prediction for what you think that area should be. Now note that this right here is a 1 by 1 square, so don't guess that it has an area of 50, that'd be weird. So go ahead and pause the video, make a guess as to what you think the area is. All right, so if I was gonna make some sort of guess, I'd say like if I look at like this, if it went directly across, that'd be like half of that square. So I know that the area should be something less than 1/2, but I'm not quite sure how much less than 1/2 it should be, just like a little bit less than 1/2. So we're gonna go ahead and look at 3 different ways that we can find the area underneath a curve, okay? So we're gonna go ahead and we're gonna draw this picture several times today. We're gonna go ahead and draw it again. It'd help if I did a better job drawing it. Okay, and one way that you can find the area underneath the curve is to take that part underneath the curve and divide it up into small rectangles, because we know how to find the area of a rectangle. So what I'm going to do is I'm going to take this right here, if this is 1, then this is 1/4, 1/2, 3/4, and I'm going to go take this line right here and go up and see where it crosses that curve and go over, and there's a rectangle, and take this one and go up and see where it intersects the curve, go over, there's another rectangle, take this one, go up, over, there's a rectangle, that one already intersected the curve. So as you can see, this area would be an overestimate, but at least we could find the area. So what we did is we used 4 rectangles and right endpoints as as the heights of the rectangles. So what I mean by that is that when I drew my rectangles, the right corner of the rectangle is what showed up on the curve. So I used the right edge, and then I drew my rectangle over, used the right edge, drew my rectangle over, and so forth. So the way that we write this out to show the math that we did is we're going to say R sub 4. So I used right endpoints and 4 rectangles. The width of my area for this, it's going to be width times height, or width times length, I guess. So we're going to have a width of 1/4. And then the height of the rectangle would be calculated as the y-coordinate of the curve. And the y-coordinate of the curve is what you get when you do 1/4 plugged in here. So y equals 1/4 squared. So there we have length times height, I guess. And then, or width times height. So our next width, again, is going to be 1/4. The height here is going to be whatever I get when I plug in 1/2 to the curve. So 1/2 squared. Again, a width of 1/4. This time the height is when I plug in 3/4. And then a last width of 1/4. And the height is what I get when I plug in 1. So we can shorthand this a little bit when we plug it into the calculator by saying 1/4 was the width for all 4 of the rectangles that we had. And then first we had a height of 1/4. Then we had a height of 1/2, then we had a height of 3/4, then we had a height of 1. So if I go ahead and plug that into my calculator, and you guys are going to get very quick at plugging in this sort of thing. So 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. We get 0.46875, which is 15/32. And again, like I said before, we can see that that's an overestimate because our rectangles went above the curve. So 0.46875. Okay. We can also do the same process, but we can use left endpoints. I keep drawing the curve like that. Okay. So this time, the height of my rectangle is going to be found by looking at the curve on the left side. So my first rectangle is actually nothing. My second rectangle would look like that. There's my third and my fourth. I had to remake this video from last year because last year I kept saying triangle. But I haven't messed up yet. Knock on wood. Okay, so this time we used 4 rectangles. I know it looks like there's only 3, but that's only because this one right here has a height of 0 since we're using the left endpoints. Okay, so here we're going to say L sub 4 is 1/4 for the width. The height is the left endpoint, so we get the left endpoint from plugging 0. The left value, we're going to find the height from plugging that 0 into the curve, so 0 squared. Width of 1/4. This one would be 1/4 squared. Another width of 1/4. The left endpoint here is 1/2. We get the height by looking at 1/2 as it's plugged into the curve. So 1/2 squared. And then the last width of 1/4. And the height for this one would be 3/4. So if I want to shorthand that, I can take out the width of 1/4 because it was the same for all of them and then say 0 squared plus 1/4 squared plus 1/2 squared plus 3/4 squared. And if I don't want to plug that all in again, I can just pull this down. So 1/4, 1/2, 3/4, instead of 1 squared, we've got 0 squared. So I took out this 1 squared right here, and I replaced it with this 0 over here. Okay. So that gives me 0.21875. Which is 7/32, quite a bit smaller. And as you can see from the curve, that's definitely an underestimate because we have all these little kind of triangular shapes that were not counted as part of the curve. All right, so as you can guess, the better option would be to use something that's kind of like in between a left endpoint and a right endpoint, which would be to use the midpoint of the rectangles. So that's what we're going to do next. So when we do these areas underneath curves and we use rectangles to find them, what we're doing is we're calculating Riemann sums, and Riemann sums can be used, can be found using left endpoints, right endpoints. We have subintervals of 4 where we're taking the entire interval and we're dividing it up into 4 equal pieces. You could do subintervals of 6. The more subintervals you have, the more accurate your answer is going to be. Obviously, like infinitely many subintervals would have been the best, but you'd be here for a long time. So again, I'm drawing the same shape. I'm dividing it into 4. And this time we're going to think about midpoints. So when I draw my rectangle this time, I'm going to say, here's the middle. And then there's my rectangle. There's the middle. So you can see that when I draw my rectangle, I have a little bit that's an overestimate, but I also have a little bit right there that's an underestimate. So the idea is that when you do these, you're kind of balancing it out. A little bit over, a little bit under. Get the middle. A little bit over, a little bit under. Okay, so I'm going to go ahead and label my intervals. I've got 1/4, 1/2, 3/4, 1. So I'm going to write off to the side what we're doing. We used 4 rectangles and midpoints as heights. Okay, so M sub 4 is a width of 1/4 for the rectangle, and then the height would be the middle of 0 and 1/4. So halfway between that would be 1/8. And to get the height, I'm taking the 1/8, I'm plugging it into the equation because that 1/8 is a point on the curve, which means it's a y-coordinate. So 1/8 squared. Then this is 2/8, so the next midpoint would be 3/8. So plus 1/4 times 3/8 squared. 4/8, the next midpoint would be 5/8. And then 6/8, and the next midpoint would be 7/8. And again, we can shorthand it like we did the other ones. So 1/8 squared plus 3/8 squared plus 5/8 squared plus 7/8 squared. So it's going to be very important that when you plug these into a calculator, you're getting all those parentheses in there. If you're doing a fraction raised to an exponent, you do have to have parentheses around that fraction. So I'm not going to show you myself typing this one in because you don't need to see it again. But the decimal we get here is 0.328125, which is 21/64, and is actually very, very close to the exact answer, but it's a little bit under. All right, so how can we get a better approximation? You can have more rectangles. So 6 rectangles, 8 rectangles, 10. You could do 9. You could do 15. The battle here is how many rectangles can you do, but knowing that you have to add them up one by hand, which is the frustrating part. So this is kind of why we have a reason to streamline this process and to make it more accurate. The actual area for this problem is exactly 1/3. And we will get in the mathematics behind that later. Okay, so now we have to take what we just did and we have to formalize it a little bit, because if we were doing 20 rectangles, we would not want to write this out. We would want to have a way to shorthand it. So I'm going to show you guys how we do that. So first, we're going to go ahead and write down the formula. So we're going to say the area, the R, goodness. The area A of the region that lies under the graph, or under the curve, so the area A of the region that lies under the graph of a continuous function is, and here's the formula. We have the limit as n goes to infinity of delta x times f of x1 plus f of x2 plus f of x sub n which is the limit as n goes to infinity of delta x times the summation as I equals 1 to n of f of x sub I. Okay, and I'm going to define a few things, and then what I'm going to do is I'm going to relate this back to what we just did. Okay, so we have to define how to find a few things here. Delta x is b minus a over n. N is the number of rectangles. Xi is delta x times I plus a. Okay. So we're going to write an example with this. We're going to write the area under y equals x squared on 0, 1 as a limit. Okay, so, oh, sorry. Write the area under y equals x squared as a limit. So I'm going to write down again, and you should too, what we had written down for our right endpoints. So we had 1/4 times 1/4 squared plus 1/4 times 1/2 squared plus 1/4 times 3/4 squared plus 1/4 times 1 squared. So what we're going to do is we're going to kind of go back and make this fit what we just looked at. So this 1/4 came from us figuring out what our delta x was. We said that our delta x was b minus a divided by the number of rectangles that we had. So we had 1 minus 0 divided by 4 rectangles gave us 1/4. All right, so you guys can see that this number right here was actually our delta x. right? So what we did, if you guys recall, is we took that delta x out in the front, and then as a GCF, and then we had 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. So you guys can see that this matches this notation. There's our delta x. Here's our f of x1, f of x2, f of xn. So if we want to shorthand this, we can say you're adding up a bunch of things, right? That's the summation notation. So we're adding up a bunch of things. We have our delta x that's pulled out in the front, and then the summation of all the stuff in the parentheses. But if we could write down how we got the pattern of these numbers, that would be easier to just write the pattern, and then we don't actually have to write out all those numbers, right? So the way that we write down the pattern is we say x sub I is delta x times I plus the a value, all right? So x sub I is delta x, which was 1/4, times I plus the lower bound, that's 0. All right, so we have xi is 1/4 I. Okay, so this means basically that you start at 0 and you add 1/4, that's your first one. Add another 4th, that's your second one. Add another 4th, that's your third one. Add another 4th, that's your fourth one. All right, so and it's a function, it's whatever function you plug it into. So the function we plugged it into was x squared, which is why when we write ours, we're going to have squared, 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 squared. Okay, so the way we're going to write this as a limit is we're going to say the limit as n goes to infinity. We had 4 rectangles. Now we're saying that we have infinitely many rectangles. That's how we would find the exact answer. So we're going to say this is 1 over n. And then we have the summation when I is just 1 all the way to n. So we're saying the first rectangle, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, the 10th, all the way to infinity. And then the function that we're plugging it into is x squared. So we're going to have 1 over n times I squared. So for us to do 4 rectangles, we use a 4 here and a 4 there. And we plug in 1 for I, then 2, then 3, then 4. And that gives us our 4 terms. If we did 6 rectangles, we would do 6 here and 6 there. And we would have 1/6, 2/6, 3/6, 4/6, 5/6, and then 6/6. All right? So this is how we write this as a limit. And what you'll notice is that with integration, we are defining it, that idea of finding the area under the curve, we are defining it as limits, which is exactly the same idea as what we did with derivatives. We defined it as limits first, and then we went through and we found some shortcuts and we started working with those. So we're doing the same thing now that we're doing integration. We're starting off by defining integration using limits. We're adding up rectangles, infinitely many of them. So here's our limit definition. And eventually we're going to get to where we have some shortcuts that we will primarily be working with. But all of it comes back from this. So limits, adding up infinitely many rectangles to find the area underneath a curve. Okay, so here, off to the side right up here, this is our formula. We're going to say this stuff right here is the limit of sums of areas of rectangles. All right, and when you have a specific number of rectangles that you're finding and you're getting your estimation of the actual answer, that is called Riemann sums. So that's when we have 4 rectangles or 5 rectangles.